Hey everyone, welcome back. Today we have RMM Shortlist 2018 and 1, where a problem is you ought to determine all polynomials f with integer coefficients such that f of p is a divisor of 2 to the p minus 2 for every odd prime p. So, let's go. So factor out the 2 right away, and I guess the first thing I can do is I can automatically plug in certain small values where let's say f of 3 divides 2 times 2 squared minus 1, so it's 6 3. So there's some number of values here and some number of values here. 2 2. Okay, so what do we think the answer is? Probably 2 and constants. Please do stuff faster. After 20 minutes, I'm having my geography test. We will try to solve this in 20 minutes. Oh, sorry, not 2. P, identity, P, and 2P, and constants. I think in general, I'm gonna say, I want to go if f of 0 is not constant, then if f of 0 is not 0, then f is constant. Is probably some. Can you prove random polynomials are too large? I don't think so. The f of p is probably, f of p grows at most polynomial in p, so it's always smaller than exponential for large p. F of 0 is not 0. Maybe that's not what I want to do. So what can I say about divisors of 2 to the p minus 2? Let f of 0 equals x. Well, you can't plug in 0, right? Oh, I see. Proof. So by Bertrand's postulate, there exists a prime. So suppose f of 0 is, let's say it's c. By Bertrand, there exists a prime p such that c is between c, p to p. And so f of p equals so this should be bad, because we'll have f of p is congruent to f of 0 is congruent to c mod p, and f and 2 isn't an odd prime. Oh shoot, the problem says odd prime. F. No, actually this doesn't break. I was hoping it would break. Dang it. Okay, never mind. Bertrand is the thing that says there's always a prime between n and 2n for n. Okay, maybe I'll go. Yeah. Bertrand can't work for c equals 1. I mean, I was assuming we'd probably just take care of c equals 1 manually, because it shouldn't be hard to roll a particular small case. F of 0 equals 2. Yeah, that's fair. So what if f of p, let's say there's some odd prime q that divides f of p. Suppose q divides f of p, where q is an odd prime. What I'm gonna do is I'm gonna find another prime. So look at all the primes. P, we'll call it p prime. No pun intended. Such that p prime is p mod q. Then you can get some divisibility result here, right? Thank you, Merzu9 for the follow-up. So on the one hand, we have f of p prime divides 2 to the p prime minus 2, which I'll actually write as p plus kq minus 2. And on the other hand, f of p prime is supposed to be, since q divides f of p and q evenly divides both p and p prime, this should work. Oh, this should work. So forget the f0 thing. I think that's just garbage. I like this line a lot better, where it's like, okay, suppose I have a prime, like take literally any prime information. This is like, you know, this is all the information you have. Like this is a maximally generic situation. Then I look at the primes here, p prime, and then I get this statement where this thing I'm assuming is p prime, but this thing is also divisible by q because it's also 0 mod q. So this looks pretty bad, and the reason this looks pretty bad is because this is like 2 to the p times 2 to the q to the k, which is... So we know that 2 to the p is 2, that's given to us, and we know that 2 to the q is 2 by Fermat. This is k. So this is looking really bad. This is all modulo q. This is looking really bad because it doesn't look like this thing should be divisible by q in general. There's no reason we expect k equals 0. And in fact, what I'll do now is I'm going to go here and we'll modify this so that this, instead of being q squared, let's say this is just like p plus q mod q squared or something. So like k equals 1 mod q or something like that. So let's write what this is, q squared. Yeah, actually, I was going to rewrite the notation, but there's no need. I think it makes it more confusing. So p prime is like p plus kq, where k is 1 mod q. That's what this means. And now this k is actually exactly equal to 1. So now I should comment on why this is possible. It's called Dirichlet theorem. That's basically what's happening. So as long as q is not literally the same prime as p, then Dirichlet theorem promises that you can find primes which are an arithmetic progression. Basically, Dirichlet theorem says that like if you had an arithmetic progression where there could be primes, then there are primes, and the distribution is what you want. So this is 2, and that's really bad. So this is contra. So the conclusion of this is that for any odd prime p, f of p contains only 2 and p. And this should be set, you know, so there's at most one factor. At this point, we basically should be okay. So not every atomic 0, 1, or infinite primes. Okay, well, when I say could, I mean like, sorry, could contain more than one prime. I'll put it that way. So in particular, also there's at most one factor of 2. And so, oh, we're not quite done actually. I need to say something about I need to rule out things like p squared, and that's actually quite hard to do, I think. Okay, so let's save this what we have here. F equals 6 works too. F being like the constant 6. Seriously? Oh, jeez. Oh, jeez. You're right. 6 is an issue. Why didn't my proof pick up 6 here? What did I mess up here? Check q equals 3. What did I do? Oh, no, 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 no. Exponent reads q minus 1. Mod q? I see, I see, I see, I see. I see, okay. You are all correct. So q times q minus 1. Ah, that's dicey. Okay. Okay, so what's it? Let me think through what the Dirichlet I want is. Rather than write it this way, I want to say prime, so p prime is p mod q, and the condition I want on k is I want k to also be, let's say 2 mod q minus 1. I think that should be okay. So when I calculate these, I get some condition mod. I saw the end one, so I thought I could swash it. I mean, I feel like I kind of know where it's trying to go. So is k equals 2 mod q minus 1 work? So it's like p plus 2 mod q minus 1. I just need this to not be 0. So the mod q minus 1 means that I want p prime to be congruent to p plus 2q mod q minus 1. That seems really bad, actually. Because I can't control the prime factors of q minus 1. But on the other hand, there's no way they're always 0. I feel like the opening has to be along these lines, though. So, like, I need some small number that is congruent to... You know what? Forget k. Let's just control p prime modulo q minus 1. So I can put anything here which is different from... Yeah. I don't need to think specifically about... Okay, so we're okay. We're mostly okay. So, yeah, this is fine. So, for my favorite integer r, r? Do I want to call it r? Let's just call it, t. We'll call it e, okay? And we'll put an e here. So what's the conclusion? The conclusion is for every e relatively prime to q minus 1, we have q divides 2 to the e minus 2. So this shouldn't happen for most primes q. Like for most primes q, This should force Q at most 3. Yeah, that's fine. This should force Q at most 3, and the reason is that it means that 2 has the property that is it Q minus 3? We can take E equals Q minus 2, right? Okay, that's the cleanest way to do it, I think. Just take E equals Q minus 2 to get Q divides like 1/2 minus 2. There we go. Okay, so amended conclusion because I screwed up. Now we fixed it. This exponent is supposed to be mod Q minus 1, not mod Q. This is why I do this on a stream with viewers so that I don't make myself look too stupid. We get f of p contains only 2's, 3's, and p's. There's at most one factor of 3, and well, there's at most one factor of 2 always, and let's see a reps. Is it repzam? Yeah. Yeah, sorry. Today was a stream with a lot of technical problems. I guess I have a lot of those. I think we've gotten the main part of the problem though, which is the good news. See ya. My geography test is also going to glitch, I know. There's still a decent bit left, I think. Okay, let's work it through. So, what I want to do now is I want to constrain the number of 2's, the number of 3's, and the number of p. The number of factors of p is going to be the toughest part. For sure, I think. 2's and 3's I'm not too worried about. Well, we're already done with 2. At this point, like when I say... Let's look at like f5 or something, right? f5 divides 30. So at most 1/5 in here. Not at most 1. Sorry, at most 1/3. And f of 7 is supposed to divide 128 minus 126. That is 2 factors of 3, so I don't want that example. 13? Is 13 good? Basically, my strategy. Okay, let me first show that it's never divisible by 9. My strategy for show it's never divisible by 9 is for every. Can I do that? For every residue class mod 9, like 1, 2, 4, 5, 7, 8, it suffices to exhibit a single number which is provably not divisible by 9. Is that correct? So let's kill factors of 9. Why does this generalize to all p? I haven't claimed that yet. I'm just playing around right now. But right now I'm trying to say like oh jeez, this requires me to plug in numbers. Does it? Wait, I can do this without plugging things in, right? Right? Maybe? I mean, there's no need to optimize this calculation though. So every odd prime other than 3 is f. $17. $3. Okay, I'll just do, okay, you know what? I'm gonna try to be smart about this. This is too annoying. For every p mod 9 can find a prime p prime such that p is not, oh shoot. Am I gonna get stuck? They're always odd. Yeah, no, it's fine. So I want them to be congruent mod 9 and p prime is not 1 mod 6. Is that possible? I feel like I'm getting stuck. I want p prime to be like for 7, what's the thing I'm using? If I go up and I want to use like, no, this doesn't. It's 1 mod 3, so anything that's going to, no, okay, so something's wrong. You can get factors of 9. Like f of 7, etc. could have factors of 9 in it. That's not good. That's really bad, actually. That's incredibly bad. Really? Yeah, if p is 1 mod, you're right. A prime being 1 mod 6 will always have 9 divised to the p minus 2. Okay, so I need to think about something else. At the very least, like once, if I know that f of 3 is even versus odd, then I know the parities of all of them, right? So let's just assume, let's just assume that f of p is even for all primes p. So we're basically at the situation where f of p is equal to p 2 times some power of 3 times some power of 3 times some power of I feel like this is the situation where I should just start talking about this. Like, it feels like there's no polynomial that has this property, period. Even with real coefficients, even if I ignore the divisibility. Or something. Right, the numbers are too sparse. Maybe try A minus B. I'm unsure that we can get more information out of that. I feel like I used this already, and like I can't even, if I can't even get rid of 9s, I don't see why I can get rid of things using that. Thank you, Snurf33 for the follow. I think instead what I just want to say is like, oh no, but because there's 2 parameters, it can kind of mess with the size. Okay, well, you know what? Here, let's do this. Let's focus only on primes which are 5 mod 6. So then v3 for those primes. So since f of 5 has v3 less than or equal to 1, we have AP at most a is between 0 and 1. Okay, and then let's let... So suppose f of x is like c times x to the degree plus lower order terms. Yeah, I feel like this should just work for sizes at this point. Like I have a polynomial, so eventually it has to the b of p should be eventually constant and therefore actually constant, is the idea. Specifically, if I divide by p of d, and now I'm treading on dangerous water, but that's okay. Analysis. So on the one hand, f of p to the p of the d is equal to the p to the b of b minus d times... Well, we'll write like 3 to the... It seems like you can easily rule out the constant term. How do I rule out the constant term? Because for large p, the term must be a power of 3 and 2, but it can't for some p. I had the same intuition, but I don't see how to make it work. Like, I felt like I should... Like, actually, like, f of 0 was the first thing I looked at, but I couldn't get anything out of it. Because the only relation between f of p and f of 0 is that they are both divisible by p. Or they are congruent mod p. Oh, okay, so like, if f0 is non-zero... Like, you take a large prime that doesn't divide f of 0, you look at f of p, it's also not divisible... Actually, you might be right. I think you might be right now that we're this constrained. let's take P to be, yeah, okay, yeah, let's take P to be a large 5 mod 6 prime. Not dividing f of 0. Yeah, okay, this is I like this. I think we can get rid of the 9s this way. Actually we can get rid of most of them this way. Let's take P to be a large 5 mod 6. Okay. I think Chao might be right. Then f of P is not divisible by P. So why did we not try this earlier? Earlier we didn't have enough information yet. Okay, that's the issue. Like now that we've have this restriction about 2s and 3s, I think the f0 thing will work. So fp is non-zero mod P. So f of P has to divide 2 times 3 to like some power. It must be of this shape. But 2 to the P minus 2 is congruent to what, like 3 mod 9, and 2 to the P minus 2 is 2 mod 4. There we go. So conclusion, either f is constant yes, also f of P divides, so to be explicit, this means f of P divides 12. Therefore either f of f is constant or f is divisible by x. If f of x is divisible by x, redo problem with f of x over x. Okay, so yeah, I think the analysis thing that I was doing would have worked as well, but this is much cleaner. Hence f of x is, so repeated whole constant. So f of x is like cx to the d to some exponent where c, the constant, the leading coefficient is either 1, well it divides 12. And manual check that, I guess like 6x barely doesn't work because of the prime 3. So I almost feel like this problem would have been, oh actually you have to cut it off at some point. If you forbid 3, then some other weird stuff might happen. So manual check then 2p, 2p, and factors of 12. Factors of 6. What? Wait. What? It's 6, not 12. Our solutions. How do you cause it divisible by x? So suppose you take a large P. Consider large primes 5 mod 6, which don't divide f0. For these primes, f of P is no. What happens is if f of 0 is non-zero, you take the prime P, and f of P is non-zero, so f of P blah blah blah. So f of P divides 6, and because you have an infinite supply of 5 mod 6 primes, you find that you have an infinite sequence for which like f is equal to a factor of 12. By pigeonhole it, you narrow down to a quarter of those values so that it's a particular factor, and therefore f is constant. Yeah. Okay, we did it. Okay. Yeah, the F0 thing is good. Alright. Oh, easy. Alright, for those of you on YouTube, thanks for dropping by. Hope you enjoyed the problem. See you next time. Those are some big emoticons.